Hi, I am Annalise. In this video, you will learn about polar coordinates
with double integrals. Thank you.
I am Loizada.
Yes. Okay. All right. So we're going to do a change of variables into polar coordinates in our double integrals. So I've written down here the rules for converting between rectangular and polar coordinates. If you don't remember that, you can go back and look earlier in your calculus textbook. I want to look at a couple regions just as a warm-up. So for example, let's use some polar coordinates to describe the region. Okay, so the first one I want to look at looks like a quarter circle here. I'm going to call this -2 and 2, and I'm going to shade the inside. All right, so if I want to use polar coordinates, I've got to get bounds on r and theta.
Now we can exit you.
Okay, so think about a point in this region has the form r comma theta, where this is my angle theta, and r is the length of the line from the point to the origin. Okay, so looking at this, you can see that r goes from 0 all the way out to 2. So my bounds on r are 0 to 2. And theta here, I'm going to start on the positive y-axis, and as my points rotate, they're going to go this way. So think in your radian measures. This is 0, pi over 2, pi, 3 pi over 2, and 2 pi. So here theta is going to run from pi over 2 to pi. Okay, so we could describe r as the set of all points, r comma theta, such that these bounds hold, right? 0 is less than or equal to r is less than or equal to 2, and theta is between pi over 2 and pi. Okay. What about this region? So I'm going to draw a circle and a bigger circle, and I want the annulus that we get by taking the region between those two circles. And let me label some points. This is going to be 2 and 2. This is going to be 5 and 5. Obviously, I haven't drawn it to scale, but there you go. Okay, so now let's think about what my bounds on r and theta are. Here, if I'm looking at a point, r is going to run from 2, let me use the laser, from 2 to 5. And theta, well, this time I need to go all the way around, right? So theta is going to run from 0 to 2 pi. Okay, and you could write it in the same way that I've written that one. I'm not going to bother doing that for the sake of time here. All right, these are called polar sectors. They have the form r equals r comma theta, where r is bounded by 2 real numbers and theta is bounded by 2 measurements of theta. Okay, so I want to take a double integral dx dy and convert it to polar coordinates. But we can't just switch out the dx dy for dr d theta. So I can't just change the variables and call it good. I've got to think about what's happening with the picture. So let me sketch a little picture for you. And we'll think about what's happening here. Okay, so suppose I have two functions, polar defined functions, r equals g1 of theta, and let's say r equals, so r, equals g2 of theta. And we're looking at those functions, say between theta equals alpha and beta.
And beta.
You can't do that.
Okay.
All right. So, Annalise is going to be quiet while we finish doing this. Seriously. Okay, so I'm looking at this region here. All right. Now, the idea is I want to cut it up into a mesh of radial lines and curves. Okay. So think about your polar graph paper, and I wish I just had polar graph paper here, but I don't. Think about what's happening with your polar graph paper. Let me see if I can try to draw this nicely. In your polar graph paper, you've got circles. Oh, that's a terrible circle. Let's try this. Oh, boy. All right, so it's filling it in. Oh, that's okay. Well, you can get the picture, right? Oh, no, that's bad. Okay, so I've got my circles, and I've also got these radial lines that are going out r units along those radial lines. Oh, boy, let's not do that one. Okay, something like that. All right, so I've broken this into a mesh of radial lines and arcs, right? So a section here, let's zoom in. What's happening here? Well, these are changing by some change in r, delta ri. And I'm going to call a point in here, say, ri, comma, theta I. Now I'm going to focus in on one of these little sectors. So let's do a little cutting. Copy. And let's look at it over here. Oh, I didn't want all that. Oh boy. All right, let's just draw it. Okay, so it looks something like this, right? Where I've got two arcs here. And so if I wanted to know the length of those are going to be r naught change in theta. That's just the arc length. Remember, arc length is S equals alpha r. I've written it backwards, r alpha, but. And over here I have ri delta theta, so change in theta, where change in theta is the change in these radial lines, right? Okay, so that's what's happening on these arcs. What's the length here? Well, this is my change in r, which is real tiny. You can see it over here, right? Change in r. Okay, now the area of this blue shaded region is going to be the sum of the areas of these little pieces that kind of look like rectangles, but they've got these little arcs. But I can take the mesh so small small enough so that R naught is approximately the same as Ri. And so let's just call that R. And then that will mean that my piece is a rectangle, approximately, with area. Well, the area of a rectangle is side length times the opposite side, not opposite, the adjacent side length. So I get R, change in theta, times change in R. Okay, so that's approximately my change in area. Okay, now if we take it small enough, all of those delta variables we can think of as dA. So delta A is dA, delta theta is about dr, delta r is about, I said that backwards, delta theta is about d theta, delta r is about dr. And so what this means is that dA, which is what we see in our double integral with rectangular coordinates, is equal to r d theta dr. Okay, so when I go to convert to polar coordinates, I want to use this. Okay, so I'm going to turn the page and write that out. Okay, so the volume of the region given above, one of these rectangles, approximate rectangles, is, well, if I'm looking at a function above that region, I'm going to take a point in that region and evaluate it, the function at that point, and then multiply by the area of the rectangle, which in polar coordinates, well, I replace x with r cosine theta, so ri cosine theta I, and y with ri sine theta I, and we just said delta A is r dr d theta. Okay, so that's going to be our conversion in our double integrals. So if I want to go from a rectangular double integral to a polar double integral, I'm going to go from alpha to beta, or my bounds on theta, and from, let's call it g1 of theta to g2 of theta are my bounds on r. F of r cosine theta, r sine theta, r dr d theta. All right, so let me make one more caveat where theta is bound by alpha and beta, with 0 less than or equal to beta minus alpha less than or equal to 2 pi. Okay. All right, so our goal in this section is just to use this. I'm going to pause this video, and in the next video, we'll do some examples.